Hello, good afternoon. Today I'm going to talk to you a little bit about the Doppler effect. The Doppler effect is the last phenomena that we'll look at for waves in topic 9. This is topic 9.5. And I appreciate you taking the time to spend with this topic as we are missing a day of class due to the elections that are taking place. I'm going to shrink my window down just a little bit here. I will hopefully be able to cover most of the things that you'll need to know about the Doppler effect in here, although you'll want to practice some problems on your own. And I also won't do the derivations of the Doppler effect equations, which is really something that I would encourage you to do. But I will be able to talk about what is meant by the Doppler effect and help you see how wavefront diagrams can explain how the moving source and moving observer situations can be understood in terms of the wavelength changes and frequency changes that will be seen. We will go through a problem involving the Doppler effect for sound, a relatively sophisticated one. And we'll talk qualitatively about the Doppler effect for light, which has some applications including like speed radar, and also is significant because it allowed for the observation of receding galaxies and the red shift or blue shift that tells us how objects are moving away or moving towards us in astronomy. In order to really understand the Doppler effect, we have to go back to the way that waves propagate. And just a little bit of terminology here. The wave fronts represent the crests or troughs in the media for the disturbance of the wave. In the case of the Doppler effect, we're looking at sound waves. So these are the compression areas or rarefaction areas that propagate outwards along rays. We're going to be looking at curved wavefronts that are coming off of a moving point source. But sometimes when it's far enough away, we'll be thinking about those as plane wavefronts. If thinking about wavelengths and frequencies and the way that they're connected in terms of the speed is unfamiliar to you, you may wish to review some of the demonstrations in the Fallstad wave tank. We'll use the Fallstad wave tank to look at the Doppler effect in just a moment. So the Doppler effect is something that you've almost certainly heard, if not heard of. It's the phenomena that you experience a changing frequency when the source of waves is moving towards you or away from you. Most people remember the experience of having a car blaring its horn driving past them, where the horn goes from a high frequency as the car is approaching you to a lower frequency as it's moving away from you. You'll hear something like "brrrr" as a car goes past very quickly. The increase in frequency or the decrease in frequency is what we refer to as the Doppler effect. This is the moving source of waves, Doppler effect specifically. The spacing of the wavefronts changes when a source is moving, and so the wavelength is not constant for observers at different locations. And we'll look at a simulation now to observe that the wavefronts remain circular and centered on the source, but the wavefronts get clustered together in the direction of motion or spread out in the direction of motion. And the other thing that's just important to remember, and I'll remind you of this when we come back to this slide, is that the amplitude of the wave isn't changing here. This is not a change in amplitude, it's a change in frequency that's observed. So I'm going to hop over to the Fallstad ripple tank. There's a link here. And what we're going to look at is example 1 of the Doppler effect. So just to let you know what we're looking at here, we have a probe. The probe is placed here along an axis where our source of waves, the source of these circular waves, is moving back and forth. And on the probe, I can see what frequency I'm observing. I'm going to pause this in a moment, but first, as we watch the source moving towards our observer, we can see that we're seeing a frequency of about 300 hertz here. Notice as the source goes past, that frequency drops to around 175 hertz. So there's the change in frequency that you would hear for a car horn as it's going towards. You hear the slightly higher frequency. Here we're seeing that again as the car is moving towards the source. As it's moving away. I'm going to pause this for a moment so that we can look at what would be called a wavefront diagram. I'm going to let the source move for just a moment so that we can see the wavefronts only while it's moving. And I'm going to go ahead and stop it here. The source is moving along this line, and you can see that the wavefronts are circular. There's a circle here, there's a circle here, there's a circle here. All the wavefronts are circular. But because of the motion of the source, this circle has its center right here. The circle above it, the blue circle, I'm talking about the crest here, has its wavefront centered on this point. This circle has its wavefront centered on this point, and this circle has its wavefront centered on this point. So the wavefronts are all circular because they're all coming from a source and moving out at a constant speed. However, the wavelength, if I were to put my observer right in front of this source, would be quite short. I'll add a couple of probes to see that. And if we look at the spacing of two probes, we have one here. You just add one more. And we can see that two probes on successive crests here are spaced. This one's at a height of, 4.79, and this one's at 3.56. So in this scale, a little bit over a meter. On the other hand, if I looked on the opposite side, the wavelength, the distance between two successive crests, is quite different. And I can look here, and now I have one at 20.51 and the other at 18.12, so more than 2 meters. So the wavelength is pretty clearly changing here because of the motion. Right? So that's what we mean by a wavefront diagram that shows the wavefronts clustered together with a short wavelength in front of the moving source, and the wavefronts spread further out behind a moving source. The Doppler effect isn't just about moving sources, it can also be about moving observers. So I'm going to switch over to the single source simulation and add a probe in here so that we can observe this one. There isn't a nicely built tool inside of the Fallstad simulation to show a moving source, so I'm going to have to do this myself. I'm going to start by moving this down to the bottom, and I'll have my source move towards. We can see what the natural frequency of this source is right now. It's about 220 hertz or so that this observer sees. And just to be clear, if I put the observer up here after the motion, we're going to see it's the same frequency, 220. Right? So it's not about where you are. The frequency and the wavelength are the same in both cases. But now I'm going to try to slowly move this towards, and let's see what happens to the frequency. Understand it's going to get a little messy because I probably can't keep my mouse moving at exactly the same speed. However, as we're moving towards, you can see that that 220 hertz is no longer the frequency. The frequency is getting closer to 300. If I think about the frequency as the rate at which those wavefronts are hitting me, the reason that the frequency is going up is clear. The wavelength is staying the same in this case, but the speed that I'm moving towards the source gets added to the speed that the wavefronts are moving towards me, and so I'm going to be encountering those waves more frequently. So I'm going to hear a different frequency. Let's look in the opposite direction. I'm going to move along away, and you can see that now the frequency is going down. Instead of 220 hertz, I'm at something like 175. This is the moving observer Doppler effect that has the same result to see a change in frequency, but a different origin to that phenomena. If you haven't had a chance yet, I strongly encourage you to play around with this, to look at these numbers for yourself. We're looking at the single source to do the moving observer, and looking at Doppler effect 1 to see the moving source. Just as a quick reminder, the Doppler effect is the change in frequency that we observe when the source or the observer are moving. It really doesn't, there can be a difference in the wavelength that we observe, but really it's the difference in observed frequency. And second, just a reminder, it's not an effect of amplitude. While it may be true that you hear a car horn increase in frequency and in amplitude as it's moving towards you, that first phenomena that it's increasing in the first phenomena that it's increasing in frequency is the Doppler effect. The increase in amplitude is probably just the effect that the car is getting closer to you, so you experience a larger amplitude. Doppler effect is about frequency. When you take a look at the equations that are associated with the Doppler effect, initially it feels quite overwhelming. Deriving these equations is really one of the great joys of being a physics student, and I'm going to give you some hints as to how to do it, even though I'm not going to show them to you directly. I've written here the equations for both the observed change in wavelength and the observed change in frequency. The lambda prime is the way that we say that the change in wavelength, and f prime is how we see the change in frequency. The first two equations are for the moving source. And the source is moving with a speed v, and there's a speed of sound of c. Notice that the equations for the source approaching and the source receding are very similar. The only difference is that we have a minus sign when we're approaching, and we have a plus sign when we're receding. When we look at the observer moving, one thing we see is that the change in wavelength doesn't exist. We saw that with the ripple tank. The wavelength is the same, it's just the observed frequency that's different. And we see a similar pattern with the changes in frequency. Observer approaching has one sign, and the observer receding has the opposite sign. Later on, we'll look at an equation that draws all of these together into a single expression and helps explain how those signs can be remembered, because unfortunately there are a lot of different possibilities here. In order to think about the moving source, I think the easiest one to derive is when the source is approaching the observer. And like I said, I'm not going to go through this all the way with you, but I do want to give you a little bit of structure to help you do the algebra and work on this. Oops, I have to move my face a little bit so you can see the slide. We consider here our source that's moving, and in this case, the picture shows it at a speed us. The stationary observer is somewhere over here, probably far off the screen. And the waves are traveling at a speed v. Normally we would call the speed of the waves c and the velocity here v, but I'll use my equations with the v and the us here to be consistent with the photo. So if we consider two successive wave fronts being emitted, there's a moment in time, that's time 0, where the first wave front is emitted. And we'll look again 1 second later. We're going to use a frequency of 1 hertz here, 1 wavefront per second. And the two things happen between this picture and this picture. The first thing that happens that you can see is that the source moves. It moves forward a distance us because the speed is us and we're moving for 1 second. So the source moves forward by a distance. The second thing that happens is that the wave front that was emitted moves forward a distance v. It moves forward a distance v because the speed of the waves is v, and there's been 1 second that's passed. If we now think about the wavelength that an observer would see standing here, he or she would observe wavefronts that are not separated by the wavelength c, c over f, because the wavefronts have been shortened because the speed has effectively changed. Having this sort of picture in mind is really the best starting point, and focusing on the change in wavelength is the best starting point for coming up with the expression lambda prime is equal to v or c minus v over f, in this picture v minus us over f. And from there, it's pretty easy to find the changed frequency that the observer sees. So I would encourage you to start with this and try to derive the expressions that you saw on the previous slide for the moving observer approaching, the moving source approaching the observer. The change is very easy for the source receding from the observer. All that's going to happen is this velocity is going to be backwards and the wavefronts are going to be further apart. So this becomes v plus u instead of v minus u. And that kind of shows you where the change in sign is going to come from. So that picture is going to help us in looking at these two expressions here. Lambda prime is equal to c minus v over f. Lambda prime is equal to c plus v over f. And the related f prime equals f c over c minus v for the approaching. F prime equals f over c plus v for receding. Quick check for the logic here. We see f prime is proportional to f. So higher frequencies experience a proportional Doppler shift. And the frequency is increased when you're approaching. The speed of sound is being divided by a smaller number as the velocity gets larger. Whereas when the source is receding, we're dividing by a number larger than the speed of sound. So the observed frequency is decreasing, which is totally consistent with what you remember from the car driving past you. In order to do the derivation for the observer approaching the source, we have it's a little bit easier because what we know is that everybody agrees on what the wavelength is because the wavelength isn't changing. The thing that is changing is that the speed of sound is going to appear to be different because the sound waves are going to be reaching me more frequently. In fact, we can observe the speed of sound to change from, in this picture, v to v plus u as the observer is approaching the source, flipping that around for the observer receding, v minus u. And again, it's pretty quick to come up with the expression. So again, one of the great joys of introductory physics is getting to do this, so I'll leave those to you. You can pause if you want to do them. I did promise that there would be a general equation, and so it is convenient to have this single expression to cover both the moving source and the moving observer. So this would be like if you were riding a skateboard towards an ambulance that was playing a siren, what frequency would you hear? Notice that the change in frequency is still proportional to f. And we have velocities for the speed of sound, v, and the speed of the observer, uo, and the speed of the source, us. Notice how at the top it's plus or minus, and at the bottom it's the minus plus sign. That's because the convention that we use is that the top sign will be used for approaching. That gives you a larger numerator and a smaller denominator, both of which would lead to a higher frequency. And the minus sign on the numerator, and the plus sign on the denominator give you smaller values. So those would be for the decrease in frequency that you hear when the source is receding from you or when you're receding from the source. Key observations here, just so that you have the big ideas. The source and observer don't agree on some wave properties due to the relative motion. There's a great video here that shows you Of course, it shows you Grammarly. Just a moment.
Did you download Grammarly?
Yes, Bobby, but I want to specify.
I don't think you can hear it because of the way that I'm doing this screencast, but this 7-minute video is fantastic. The author actually drives his car along with a microphone so that you can kind of hear these things and you can hear what the sound sounds like in the car and sounds like outside of the car. Highly, highly recommend that you watch this. Note that if you are moving along with the source, there's no Doppler effect. You don't hear your car horn any differently if you're sitting inside of your car. That's a great observation from this video. Second thing, just a reminder, the Doppler effect refers to the change in frequency. If you wanted to look at a change in intensity associated with the Doppler effect, it's a little bit more complicated the way those wavefronts build up. It can be quite dramatic. If you move close to the speed of sound, you actually have something called a sonic boom that's created as the wavefronts overlap on each other completely and increase the amplitude quite a lot. We aren't talking about that in this situation. And finally, this treatment is observing that the source or observer is moving slower than the speed of sound. If you go faster than the speed of sound, again, you have a sonic boom. Just to pop over to the Fallstad simulation to show what that looks like, you can obviously find videos of this taking place in real life. Here our source is moving faster, and you can see that these wavefronts are building up, forming a cone here of very, very high amplitude, which is known as a sonic boom. There is a Doppler effect associated with light. Working with it is much more difficult. Had we had a chance to look at the relativity unit, the option A, we would talk about the relativistic Doppler effect. Since we haven't, the idea of relativity, the big idea is that light travels at the same speed for all observers. So when we talked about the Doppler effect and moving sources and moving observers, there were situations where the speed of sound would not have been agreed upon by the two different people because frequency and wavelength combined together would give you different values for the speed of sound. With light, that's impossible. All people agree on the speed of light. And so the Doppler effect in light, we have to consider the effects of special relativity that take that into consideration. Consequently, we don't use the same Doppler effect equations for light as we do for sound. They become much more complicated. IB doesn't ask us to derive or use these. However, they do mention that there's an approximation that we can use for low speeds, meaning speeds that are much, much slower than the speed of light. And it actually turns out to be quite nice. The relative change in the frequency of light observed, in other words, the change in frequency divided by the frequency, is approximately proportional to the speed of the source divided by the speed of sound. So our change in frequency, or f prime minus f, is just proportional to v over c. And you can rearrange this to find a value for, or find an equation for f prime. It would just be f prime times 1 plus v over c times f. The increase in frequency comes when you have a source approaching, and the decrease in frequency comes when the object is receding. These are known as red shifts and blue shifts. Red shifts give a longer wavelength and a lower frequency that's observed, and blue shifts give shorter wavelengths and higher frequencies. Blue shifts are observed when objects are moving towards us, and red shifts are observed when objects are moving away from us. Note that the objects have to be moving quite fast in order for there to be a red shift or a blue shift. The ratio here for the change in frequency is v for the source over the speed of light. You are not going to see a red shift or a blue shift if somebody is running towards you with a flashlight, The speed is just far too low, so the change in frequency might be 1 part in 10 to the 8th, which is far, far too slow. But on an astronomical scale, objects can be moving extremely quickly. And we've observed that stars or galaxies moving towards observers on Earth can have red shifts or blue shifts. And observations of these shifts were responsible for some of the first theories about how the universe is expanding. Because if you look out into distant space, what we observe is two things. One, that more objects are moving away from us than are moving towards us by a pretty large factor. And two, that the objects that are further away are experiencing a larger redshift. With more space between our observer and the object that's moving away from us, there is more space to expand in between, and you get a larger redshift. It is worth noting that the redshift that was observed for distant galaxies did prompt the first expanding universe theories, but it's worth noting that physicists agree that general relativity, in addition to special relativity, is really needed to understand these cosmological redshifts, and it's a little bit too simple of a theory to apply just one of these. Right? This is a very, very basic thing. You find lots of YouTube talking about this. I did want to do a problem with you that has to do with Doppler radar. Doppler radar is a tool used by police officers to enforce traffic speed limits. I'm actually going to do a modification of it because Doppler radars actually tend to use light lasers as opposed to sound waves. But I want to be able to use our Doppler equations. So we're going to pretend that we're using a sound wave of 15 kilohertz being emitted from one side of the radar gun. And it's emitted towards an approaching car. So you can see these waves going this way. Here they're correctly labeled as microwaves. The car reflects some of those waves off that are received by the gun that then also measures what the frequency is. The frequency is going to be increased to 16.1 kilohertz. And the question is both why does this happen and what does this change in frequency tell us about the speed of the car? First off, we can see that Doppler radar works by, oops, I'm going to move my picture again. Doppler radar works because the source is emitting waves towards a moving observer. So if the detector were on the car would see higher frequencies depending on how fast it was moving. We have our Doppler equation for doing that. However, not only does the car observe waves, it also emits waves reflecting them backwards. As it's reflecting those waves and the source of those waves is moving, because the car is the source, there's a second Doppler shift associated with the waves before they return to the original radar gun. So we have two pieces that are happening here. In part one, we think about what does the car hear? What's this Doppler shift being experienced? Well, the source is at rest. The source is the radar gun. The frequency is 15 kilohertz. The speed of sound is 340 meters per second. And the observer is moving towards at velocity v. So we use one of those first equations where the observer is at rest. The observer is moving. The source is at rest. So we have f prime is equal to the speed of sound plus the velocity of the observer divided by the speed of sound times the original frequency. Substituting in numbers just for clarity, we have 340 plus the speed of the vehicle divided by 340 over 15 kilohertz. Note we check to make sure that the sign makes sense. This is going to give us a value that is larger than 1, increasing the frequency. And since the observer is moving towards the source, we expect that they're going to experience a larger frequency. So this makes sense. And we feel good that we've picked the correct sign here. Continuing on, we think about what does the receiver over here hear? Well, the car is reflecting the sound waves. The sound waves that the car is reflecting is this modified frequency, f prime. So I'll put the equation here again, just onto this part of the page. 340 plus v over 340 times 15 kilohertz. As a source, it's moving at velocity v towards a stationary observer. So the modified frequency that the radar gun will hear is the moving source equation times the first changed frequency. So I have c over c minus vs times f prime. Notice the minus sign here is the correct one because this is the source moving the source moving towards the observer is going to cause an increase in frequency. Substituting in values to the first part of this expression and substituting in the expression for f prime to the second part of the expression, I see that there's a cancellation of the speed of sound. The c in the numerator here and the c in the denominator here cancel. And I end up with an expression that the 16.1 kilohertz that the radar gun operator observes, that f double prime, is equal to 340 plus the speed of the car over 340 minus the speed of the car times the original frequency of 15 kilohertz. And the similarity of this general form, or the similarity to the general form, that you have the motion of the observer and the motion of the source, suggests that we're on the right track here. And in fact, we are. I won't go through the steps of algebra to simplify this, but suffice to say that you can find this ratio and set it equal to the ratio here. And then you have to do a little bit of manipulation to isolate v. And in this case, I came up with a value of v is 11.9 meters per second, which in most places should be under a speed limit. So just to quickly go over the outcomes again to make sure that you feel comfortable about this, well, you should now know what the Doppler effect is meant, and you should be able to think about the Fallstad simulation to say what wavefront diagrams look like and how they explain moving source and moving observer situations. You can solve some problems using the Doppler effect for sound, although I strongly encourage you to look at the examples in your text and to practice a few from the test yourself questions. In order to feel more comfortable with that. We have a qualitative description of the Doppler effect for light, same sorts of behaviors as for the Doppler effect for light, but instead we use just a change in frequency over the frequency is equal to the ratio of the speed of the source or observer over the speed of light. And we've talked a couple of situations where the Doppler effect can be used. Your text will give you a few more. And finally, I talked to you a little bit about the redshift. At this point, I've been talking to you for a while. You've maybe done a little bit of work on your own. I would strongly recommend that to finish this up, you practice a couple questions on your own and you complete those derivations. Your text will be a great support for this. When we come back in class, we will do a couple of problems, but it's a relatively simple topic to look at. Most people are familiar with the effect. And so I hope that this gets you most of the way there, and you can ask some questions when we get back in class. Have a great extended weekend, and go out and vote if you're old enough to. Take care.